We choose to go to the moon in this decade and do the other things. Not because they are easy, but because they are hard.
Godspeed, John Glenn.
Roger, 0G, and I feel fine.
Get my feet up. Okay, I'm out.
How does it feel for the United States to be the new record holder?
At last, huh?
When that baby lights, there's no doubt about it.
Liftoff. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11.
Houston, Tranquility Base here. The Eagle has landed.
That's one small step for man, one giant leap for mankind.
Hello and welcome. This is Michael Annis, and you're listening to episode 119 of the Space Rocket History Podcast. And now, Apollo Lunar Module Design, Part 3. We have spent some time on Grumman as the contractor for the lunar module, but Grumman could not do everything. They had to use subcontractors to perform tasks beyond their capability. Grumman contracted with the Aerospace Communication and Controls Division of Radio Corporation of America, RCA, in Burlington, Massachusetts for engineering support, radars, an in-flight test system, and components of the stabilization and control system. RCA, the subcontractor, was also to design and manufacture ground checkout equipment for these items. Although the two companies had worked together for years, the Grumman RCA experience with the lunar module was fraught with difficulties. Electronic components became a pacing item in the development of the lander's subsystems, causing unhappiness at NASA headquarters and culminating in an investigation by the General Accounting Office. The extremely complex stabilization and control system was the source of much of the trouble. Design had to await definition of mission requirements and planning. To complicate matters further, Grumman did not buy the total system, but merely procured parts through RCA from Honeywell, which supplied similar items to North American for the command module. There was some commonality of parts, but the lander hardware had to be repackaged, often causing lengthy delays. Communications gear was purchased from Collins Radio and Motorola in the same manner. Now, by this time, NASA Houston was getting pretty tired of this roundabout way of doing business. Houston finally decided to speed things up by supplying the television camera, originally intended for development by RCA. So, in mid-1964, the Westinghouse Electric Company was asked to submit a bid for the camera. You may recall, at the beginning of the program, the crews had been expected to perform basic repairs to electronic equipment in the lander as well as the command module, using spare parts stowed aboard the spacecraft. But by mid-1963, Houston Flight Operations Director Chris Kraft was arguing that the crew simply would not have time to repair faulty hardware during lunar module operations. Thomas Kelly, the father of the LEM, was convinced that in-flight maintenance would degrade reliability instead of improving it. This was probably true since the electronic spares would be subjected to cabin humidity even when stowed. When George Miller took over as manned spaceflight chief in Washington, he also had reservations about the plan. As a result, in-flight maintenance was deleted from the program, and the crew was to rely on operational displays and the caution and warning systems to detect malfunctions. Redundancy would be wired in with duplicate or backup components the crew could switch to, and all electronics inside the cabin would be hermetically sealed to protect against moisture and contaminants. This decision further cut RCA's role on the lunar module. Radar, tied into guidance and navigational system, was one of the hardest pieces of the lunar module to qualify. 2 sets would be used, one for landing, the other for rendezvous. Under its blanket subcontract for electronics, RCA was to design the system, manufacture the rendezvous radar, and purchase the landing subsystem. After evaluating proposals from 4 bidders, RCA picked Ryan Aeronautical Company. This was the same company that developed landing radar for the Surveyor probe. Development of the lunar module radar was not expected to be difficult, since no technological breakthroughs were required for either system. Integrating these sets with the guidance navigation system, however, was another matter. There were also problems in properly placing and insulating the antennas, getting the precise ranging accuracy needed, and overcoming the weight increases that resulted from meeting these requirements probably posed the biggest problem of all. A happy medium between optimum weight and desired reliability was elusive, and progress was practically nil. During the final quarter of 1964, the Chief of Guidance and Control in Houston warned Joseph Shea that the radar program was having trouble with weight, accuracy, reliability, thermal characteristics, and cost. Shea and William A. Lee, Chief of MSC's Apollo Operations Planning Division, began to think about omitting the rendezvous radar from both the command and lunar modules. Lee believed these units were doubly redundant, since rendezvous could be performed by the command module pilot with the aid of data relayed by the manned spaceflight network. Donald Wiseman, an instrumentation and electronics specialist in Houston, thought rendezvous could also be conducted by the lunar module crew, using ground, optical tracking, and S-band and VHF communications equipment in place of radar. Although not everyone agreed that the system should be eliminated, work was started on the development of an optical tracker. Now let's get back to the guidance and navigation system. Development started off simply enough, but turned into a complicated tangle. MIT and Houston officials wanted to use the basic command module arrangement in the LIM to avoid developing an entirely new system. After Grumman was selected in November 1962, the contractor, the center, and MIT had tried to work out a configuration for the lander. In the middle of '63, Houston asked headquarters for permission to procure lunar module guidance through existing agreements with MIT, AC Sparkplug, Colesman, Raytheon, and Sperry. But Washington refused the request, and time was lost in negotiating new contracts with these firms. The biggest delay came from a dispute over whether to use the MIT unit in the lunar module. Grumman's refusal to accept MIT's word about the reliability of their system sparked the controversy. Lunar Module manager James L. Decker in Houston shared this skepticism and asked Grumman to look into a more advanced system than the 3-gimbaled platform MIT used. Meanwhile, David Gilbert, in charge of navigation and guidance in Shea's office, insisted on getting the MIT unit into the lunar module. Grumman was caught between 2 opposing factions. Neither of the Houston officials would get the other to change his mind, and the chasm deepened. Top management in Houston and Washington then stepped in. Bellcom would study the options, consult with all parties to the argument, and recommend a solution. In due time, NASA decided to stick with MIT and announced its decision, based on Bellcom's findings on October 18, 1963. But the announcement did not completely clear the air, and some rather strained feelings developed between Grumman and MIT. Early in 1964, however, the contractors recognized the necessity of working together on the areas where development progress affected both the lunar module and its guidance system. MIT and Grumman met together to create formal interface control documents. The purpose of these documents was to come to an agreement on key points that would govern all future action by both parties, MIT and Grumman. But at the end of February, Rector reported 29 meetings between the contractors, with 200 more to go at this rate, he said, and 55 documents drafted, but almost no concessions by either party. In April, Manned Spacecraft Center managers realized that they would have to intervene to break up the logjam. At a 2-day meeting in Bethpage on the 25th and 26th of June, Shea did just that. After scrutinizing the documents, he mediated the differences and forced the contractors to cooperate. With guidance and navigation systems now progressing, let's spend a little time on lunar module mock-ups. At various stages of lunar module design, mock-up reviews were conducted to demonstrate progress and ferret out weaknesses. These inspections were formal occasions with a board composed of customer and contractor officials and presided over by a chairman from the Apollo office in Houston. Top management personnel from the NASA Office of Manned Spaceflight in Washington and from the field centers, as well as a number of astronauts, were usually present. The vehicle was thrown open for inspection, and the astronauts were expected to climb in, out, over, and around to get a feel for the craft. Here's a clip of Thomas Kelly discussing the mock-up review.
At regular intervals during the design of the lunar module, Grumman built full-size models of the machine. With these mock-ups, engineers could check the fit of systems, astronauts could practice their procedures, and NASA could evaluate Grumman's progress.
NASA would come with literally hundreds of people. They would include all the astronauts and all the leaders of the various NASA centers and their supporting cast of engineers and experts. Now, in the case of the LEM, the crew had a lot of contact with the LEM besides just flying it from inside the crew compartment. It also served as their home base when it was on the moon, and the descent stage housed all the scientific equipment. All of those aspects of the LEM that the crew would actually use had to be evaluated in the mock-ups.
We had a sling with like a big bungee that ran down from the ceiling, and what the astronaut would do would hook it onto his suit, and he would go up the ladder, ingress and egress out of the LEM. It was quite interesting, and if you ever got on one of those things, it was quite a thrill. Like jumping off of a tree into water and then bouncing back up again.
The first of these mock-up reviews was on M1, which was a wooden mock-up of the crew compartment. It took place September 16th through the 18th, 1963. In general, the cockpit layout was acceptable, although the locations of some equipment and the arrangement of controls and instruments still had to be settled. The astronauts liked the visibility through the triangle, canted windows, and the stand-up crew positions. But they wanted the instrument panel changed so both flight stations would have identical displays. About 6 months later, on March 24th through the 26th of 1964, Grumman showed its second model, called TM-1, a wooden representation of a complete vehicle. Again, attention centered on the cockpit arrangement, support and restraint systems, equipment layout, lighting provisions, location of displays and controls, and general mobility within the cabin and through the hatches. On this occasion, a number of changes were suggested. After evaluation and approval by the review board, these modifications were incorporated into the TM-1 to make up a design freeze for constructing an all-metal model. Now, TM-1 was far more than just a means to get to the next, more advanced mock-up. For several months, Grumman designers used it to study astronaut mobility and spacecraft spacesuit interfaces. Astronauts and company personnel got into and out of suits inside the cabin, practiced stowing and recharging backpacks, and checked out suit hose connections with the spacecraft's environmental control system. The most important mock-up review in October 1964 centered on the M5, a remarkably detailed model of a complete spacecraft, including some actual flight equipment inside the cockpit. Even before the inspection, its prospects for success were discussed in a senior staff meeting at Houston on October 2nd. Comparing Grumman's planned M5 review with a review held a few days before on the Block 2 command module at North American, which one official considered a good display for a salesman, but a poor engineering tool. In fact, Max Faget said that in his opinion, North American representatives should go to the Grumman School to see what a mock-up should look like. M5 was the product of 2 years of configuration studies and the lesson of 2 previous inspections. Formal review of M5 led off with an examination on October 5th and 6th by the Astronaut Corps. On the following day, MSC Director Gilruth and virtually all the management, engineering, and Apollo leaders from Houston descended upon Grumman to inspect the cabin, electrical wiring, plumbing, flight controls, display radars, propulsion systems, ascent, descent, and reaction control, environmental control systems, communication systems, structures, and landing gear, and stowage for scientific equipment. No piece of the vehicle escaped the review party's scrutiny and evaluation. The mock-up review board met on October 8th, examined the 148 proposed changes, and approved 120 of them. These were mostly minor, and none forced any major redesign. M5 marked the culmination of the configuration definition. Now I want to spend a little time on how the lunar module fit in with the rest of the Apollo program. Although configuration was not settled and major subsystems development was not begun until near the end of 1964, NASA had begun taking stock of where the lunar module stood in relation to other pieces of Apollo. Structural connections between the lunar module and other Apollo hardware were confined primarily to the command and service modules and the adapter. Unlike its touchy relationship with MIT, Grumman's association with North American was smooth. Early meetings between the contractors were devoted to hardware designs and docking requirements. Initially, each manufacturer was to design and test all equipment mounted on his own vehicle. But in March 1963, North American assumed responsibility for the complete docking device as well as the adapter structure. Late in 1963, design engineers from North American recommended, and NASA approved, a center probe and drogue for docking. Stowage of the lander in the adapter was settled in October 1963 when the contractors and Houston agreed upon a truncated cone 8.8 meters long with the lunar module mounted against the interior wall by a landing gear outrigger truss. Thereafter, detailed focus on the dynamic loads expected during launch and on the development of the 4 panels for removal of the lander during flight, Grumman sent North American a mock-up to use in confirming the structural mounting and panel opening characteristics. Lunar module ground testing to prove the practicality of the design and flight testing to verify the space worthiness of the flight vehicle also had to be worked into overall Apollo plans. Gilruth stated that one fundamental requirement for mission success was employing, quote, the kind of people who will not permit it to fail, end quote. The basic reliability philosophy, he said, was, quote, that every manned spacecraft that leaves the Earth shall represent the best that dedicated and inspired men can create. We cannot ask for more, and we dare not settle for less, end quote. Now I have a clip of Thomas Kelly and others discussing the dedication of the Grumman workers.
What made people work so hard? Certainly there were rewards for wallet, ego, and resume, but the greatest reward was that the LEM was destined for greatness, and everyone who came in contact with the spidery machine that Grumman was building knew it.
There was a dedication and a drive on the lunar module program that I haven't seen equaled since. I've seen it equaled in very small groups, but we're talking about thousands of people here that were swept up in the enthusiasm and the historic importance of this endeavor.
This wasn't just another flying machine. This was unusual. It had not been done before. And I think there's something that many engineers respond to in the sense that it is at the forefront of knowledge and that there are risks being taken.
You got kind of caught up into something that you had no control with. There was a national goal to put a man on the moon, and it was something that we all just got so engrossed with and became so dedicated to or obsessed with that you would do anything you had to, go wherever you had to in order to get the spacecraft ready.
We thought we had hyped ourselves into thinking, we could do it. We believed we could do it. And there was something there. There was a pot of gold at the end of the rainbow. We could see it. We knew we were part of it, and we could see the progress we were making. And then we were all 20 years younger. At that time, the average age of the NASA and their contractors were, probably around 30, 25 to 30. That age, you believe you can do anything. You can move mountains. And we actually believe that. So we got caught up in it, and it was, we were addicted. We'd rather be here than go home.
The spirit I saw at Grumman in those days with the LEM was to almost be willing to go to any end, personal sacrifice, and it certainly was in the hours that people were putting in, and I'm sure it was hard on home life, to make it right.
The fact is that there wasn't any question in anybody's mind that we were going to make it work, that we were not going to leave 2 astronauts on the moon, and that we were going to get them back safely.
As the lander grew larger and more complex, it became, in the eyes of some observers, the most critical part of the Apollo vehicle. The many things that could doom the crew made ground testing all the more important. Reliability for the lander dictated either redundant systems or, where that was impracticable, because of weight and size, ample margins of safety. Grumman's basic plan for ground testing, set forth in May 1963, called for extensive use of test models called TMs and lunar test articles called LTAs. Additionally, there would be propulsion rigs to test propellant lines and for engine firing programs. Because the lander's flight would be brief, Bethpage engineers adopted a practice of testing hardware until it failed, to provide an indication of strength and to gather information on failure points. Ground testing began with individual parts and subsystems and progressed upward before the spacecraft was committed to flight. Bethpage came up with a scheme for testing the lander in simulated flight by powering the vehicle with 6 jet engines to overcome the pull of gravity and using a modified descent engine to practice maneuvering the vehicle. Although the idea appeared workable, it would be both costly and complex. There were also suggestions for swinging the lander from a gantry-like frame at Langley or from a helicopter or a blimp at White Sands. But after a second look, both these ideas were scrapped. Grumman and Houston hoped that the lunar landing training vehicle being developed by Bell could test some of the flight components at least, but installing extra equipment might slow the development of the training vehicle. A few flight instruments and the hand controller might be incorporated at a later date into the training vehicle, which the astronauts would use to practice simulated lunar landings. Flight testing within the Earth's atmosphere was finally ruled out entirely when Langley discovered in wind tunnel tests that the Little Joe 2 lunar lander combination would be aerodynamically unstable. Grumman had wanted some unmanned missions using the Little Joe 2 and the Saturn 1B launch vehicles before men flew the lunar lander. Houston authorized the procurement of autopilots for unmanned spacecraft, but did not actually schedule any such flights. After Miller invoked the all-up concept, which meant each flight was groomed as though it were the ultimate mission, Houston planners began to think about putting both the lander and the North American spacecraft aboard a single Saturn 1B. One Houston engineer even went to Huntsville to ask von Braun about the possibilities of increasing the launch vehicle's payload capacity, and there were some discussions about strapping Minutemen missiles, solid-fueled rocket stages, onto the launch vehicle to provide the extra boost needed. In the meantime, ground testing would have to carry the burden of qualifying the lander until the Saturn was ready to fly the vehicle, which caused some realignment of the lunar module program. 11 flight vehicles and 2 flight test articles were earmarked for Saturn development flights. NASA also decided that the first 3 flight vehicles must be able to fly either manned or unmanned. In November 1964, Shea, Miller, and Phillips decided on a tentative flight schedule. Saturn 1B missions 201, 202, 204, and 205 would be Block 1 command module flights. There was no assignment for 203 at this time. Shea told the Houston senior staff that it looked as though an unmanned lander might be flown on 206, the first flight of the combined Block 2 command module and lunar module would be Mission 207, scheduled for July 1967. By that time, the Saturn V was expected to be ready to take over the job of flying the missions. The lunar module had to be worked into Apollo facilities as well as into flight schedules. Grumman had its own testing equipment in Bethpage and on the Peconic River, both on Long Island. But the lander's propulsion system would have to be tested at the Air Force's Arnold Center and at White Sands. Fitting the lunar module into the launch complex at the Cape raised some interesting issues. One of the earliest was the rule that any vehicle flown from there must carry a destruct mechanism in case a mission had to be aborted shortly after launch. The rule was based on a philosophy that it was better to explode propellants in the air than to have them burst into flame on the ground. Houston, however, refused to put a destruct button on the vehicle that was intended to land men on the moon, with the gruesome possibilities of a malfunction on the lunar surface that could either kill the astronauts outright or leave them stranded. Eventually, the Air Force Range Safety Officer agreed to drop the requirements for the lander. A difficult task at all locations, Bethpage included, was getting ground support equipment ready to check out the lunar module subsystems. Traditionally, ground support equipment had been a problem since it cannot be designed and built until the spacecraft design is fairly firm. Because the lander was the first of its kind and changed from day to day as the mission requirements changed, Grumman was even slower than the other contractors in getting its checkout equipment on the line. Shea complained that the entire ground support equipment picture at Grumman looked quite gloomy. He insisted that Grumman use some equipment that North American had developed for the command module. The situation had improved by the end of 1964, but much work was yet to be done over the next 2 years before the equipment could be considered satisfactory. By mid-1964, both lander and the command module were beginning to experience the weight growth that seems inevitable in spacecraft development programs. Von Braun promised Miller in May that he would try to get an extra 2,000 kilograms of weightlifting capability from the Saturn V, which eased some of the pressure on Gilruth's team in Houston. Even so, the lander was getting dangerously overweight, moving steadily toward its top limit of 13,300 kilograms. Most of the weight-reducing talent in Houston was busy with the command module, whose Block 2 configuration was not as well defined at the time as the lander's. Several modifications in the landing vehicle were suggested, but any that limited either operational flexibility or reliability were resisted. Moreover, the lander was so unlike other spacecraft that projections were almost useless in estimating future weight increases. Containing this growth would be a major project during the coming year. The years 1963 and 64 had seen the lunar module move from the drawing boards to the manufacturing line. During 1965, hardware fabrication, assembly, and testing would begin. After that, it would take only a few steps to put the craft into space. But these steps, though few after the spacecraft design had been frozen, would not be easy ones. There would be several more pitfalls to overcome. Some of these problems, such as difficulty with combustion in the ascent propulsion system, for example, were resolved only a short time before the mission that fulfilled Apollo's goal of landing men on the moon. Thanks for listening to this archive episode of the Space Rocket History Podcast. If you are financially able, please support the podcast by going to the homepage, spacerockethistory.com, and clicking on the orange donate button or the Patreon link. Thanks.